We should say Happy Valentine's Day to everyone.
Oh yeah.
Happy Valentine's Day.
I'm wearing my pink shirt today. My daughter made sure of that.
All right, should I start the introduction?
Please.
Okay. So everyone, thank you so much for being here today. Welcome to today's CPAR and Dream seminar. Today, we're super excited to have David Held here as our speaker for this week. David is a professor at Carnegie Mellon University in the Robotics Institute, where he does research on perception and planning algorithms for robots to interact with challenging objects, and is applying this work to important areas such as robot manipulation and autonomous driving. Notably, his group has also developed the SoftGym simulator, which has been pretty heavily used in our research group. So we're definitely grateful to you for that. David completed his BS and MS degrees at MIT in mechanical engineering, and he holds his PhD degree in computer science from Stanford. Also, before starting as a professor at CMU, he was a postdoc here at UC Berkeley. David is a recipient of a number of awards, including the Google Faculty Research Award in 2017 and the NSF Career Award in 2021. Today, David will be speaking to us about his exciting work at the intersection of robot planning and robot perception and planning for robot manipulation. And we're also going to have time for questions at the end of the talk. And if you have pressing questions during the talk, you can definitely put those in the chat and we'll make sure that they get answered. David, thank you so much for being here, and we're all really looking forward to your talk.
Great, thanks so much for the kind introduction, and thanks for having me. So today I'm going to talk about my work on perceptual robot learning. So a robot consists of a perception system and a planning system. Now, the perception system processes sensor inputs and tries to estimate the state of the environment, and the planning system tries to decide what actions the robot should take based on the estimated state. Now, we typically divide up researchers in the same way. We have vision researchers who work on the perception side, and planning and robotics researchers who work on the planning side. And the question that I like to ask is, can we build a better system by thinking about these parts together? To clarify, I'm not proposing to merge perception and planning into a single end-to-end black box. I'm just proposing that we think about perception and planning together when designing the robot system. So one question people sometimes ask when I propose this idea is, why can't roboticists just use the output of computer vision method? And to understand the answer, we have to look at what do computer vision methods try to do. The goal of computer vision is typically to try to understand what is in an image, like detecting or segmenting the objects. On the other hand, the goal of robotics is to understand what will happen if a robot interacts with its environment. So if the robot takes this an action on this cloth, what will happen and what actions does it need to take to achieve its goal? So roboticists have different goals from computer vision researchers, and thus we need to develop new perception and planning methods to meet the needs of a robot system that has to both perceive and act. So for example, suppose the robot were to interact with this cloth and try to do some task like folding it. One question that we would want to know is, what is a good representation for this cloth that enables the robot to perform actions and achieve this task? There's different representations you can think of, and they have different trade-offs in terms of how easily we can infer them from observations or interactions, and how suitable they are for enabling the robot to achieve the given task. So how do we bridge the gap between perception and planning? My goal is to learn to manipulate novel, perceptually challenging, and deformable objects. And I believe that this requires rethinking robot perception and planning algorithms to handle these types of objects and manipulation tasks. Nice. So here's some examples of things that our group has achieved using this paradigm of perceptual robot learning. And today I'm going to talk to you about a few of these projects, and maybe you can ask me later about some of the other ones that I might not have time to get to. So I'll begin by talking about a benchmark that we've developed for deformable object manipulation, although it seems like some people in Ken Goldberg's group are already familiar with this benchmark. It was developed by my student, Xingyu Lin. And so a lot of this talk is going to focus on manipulation of deformable objects, which again, there's a lot of work in Berkeley on that, but there's a lot of good reason For research in deformable object manipulation, there's many applications of deformable object manipulation, such as cooking, laundry folding, the other examples shown here. And there's also many challenges to manipulating such objects. First, they have a high dimensional state representation compared to rigid objects that can be represented by just a 6D pose. The state of a deformable object is almost infinite dimensional. They have very complex dynamics, and they have self-occlusion, so you can't really see the full cloth that you're manipulating. You can just see the visible surface. So there's been a lot of work in this area, but if you look at these visualizations here, you see that most papers evaluate on different tasks, simulators, and robot setups. And this makes it very hard to compare algorithms to see if we're making progress. And so we developed SoftGym. It's a benchmark and set of environments built around the NVIDIA Flex simulator for different deformable object manipulation tasks, such as the ones you see here, which involve transporting or pouring water, straightening rope, folding or spreading cloth, or dropping and flattening a cloth once it's already grasped. And SoftGym is already being used by the community. Here's a couple of papers on it. And I guess Ellen mentioned Ken's group is also using it. So if you'd like to check it out, we'd encourage you to do so. And feel free to ask us if you have questions about it. So using the simulator, we were able to benchmark different methods on these tasks. And here with this black line, you can see the performance of an oracle method that assumes access to the ground truth state and ground truth dynamics. And so this is information that's not typically available to the robot, but it places somewhat of an upper bound on what you can expect a good algorithm that might be able to achieve. And here's the performance of a number of other state-of-the-art deep reinforcement learning methods that we've evaluated on these tasks. I'm not going to go through all these methods today, but one thing that I will point out is that if you look at these two tasks of spreading a crumpled cloth and folding a flat cloth, there's a big gap between the performance of the best methods that have access to only observational information and what could be potentially achieved, shown with the black line. And so these are the tasks that we're going to focus mostly on in this talk, and some other related ones. And so why does deep reinforcement learning perform poorly on these tasks? Well, here's sort of a high-level overview of what representation deep reinforcement learning methods typically use. So given an observation of, say, a cloth, a typical deep reinforcement learning method would compress this image to a latent vector and then put this latent vector into a policy to output robot actions, or combine it with a vector representation of the robot actions through a latent dynamics model to predict the next latent state. The top one is called model-free reinforcement learning. The bottom one is called model-based reinforcement learning. And one thing you might ask is, what does this latent vector capture about the observation? And is it sufficient for my task? So for many tasks, this is a hard question to answer. But for some set of tasks, we can actually dig a little bit deeper into it, which is methods that do planning in latent space. So these methods would take an observation and encode it to a latent vector, and then plan over a sequence of actions and predict how this latent vector will change given this action sequence. Then you can score these latent predictions and get a latent reward function. You can do this for different action sequences, making predictions in latent space, and you can score each one, and then select the action sequence that has the highest predicted latent score. So how well does this work? So here we tried this planning in latent space method with this task of pouring water, and you can see that actually it spilled many water droplets. But what did the method think was going to happen? We can take its plan and visualize this plan. So here, sorry, you can see the droplets that were spilled. So here's the plan that it had. It planned that it thought it was going to perfectly pour the water into the cup. And when you think about it, this shouldn't be too surprising because these small droplets of water are only a small number of pixels in the image. And so there's not a large penalty for the method to miss them. And they're also very hard to predict. So the simplest thing to do is just to ignore these small pixels. But that means that we're spilling water, which isn't very good for us. Here's another example of flattening a crumpled cloth. You can see it doesn't do a good job. There are many wrinkles, but in its prediction, it predicted a sort of orange blob without any wrinkles. And so this idea is sort of the same. The wrinkles are hard to predict. They take up only a small number of pixels. And so it's easier to just ignore the wrinkles, which leads to poor task performance. And so if you've used deep learning before, a deep learning fanatic might say here, well, of course, it didn't work. You didn't use a big enough land vector. Can we just use a larger land vector? And so Archimedes once said something similar. He said, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. His lesser well-known brother, Archimedes, once said, give me a large enough land vector and enough computation, and I can memorize any training set. Both of these statements are technically true, but not terribly practically useful. And so yes, with a large enough land vector and enough computation, I'm sure we could get these tasks to work. But the main point that we're going to show in this talk is that we can use different representations that encode more environmental structure in order to learn more efficiently and effectively. So we have this benchmark SoftGym for deformable object manipulation, which allows researchers to easily develop new methods and demonstrate that deformable objects presents a large challenge for state-of-the-art deep reinforcement learning. And we show the downsides of land vector representations, or at least our future work will make this point more clear. So given that, how do we actually do these tasks of smoothing a crumpled cloth? In this case, we're going to take a model-based approach. So we want to learn a dynamics model. Given a crumpled cloth, how should we interact with the cloth? Given a crumpled cloth, how can we predict the effect of the robot's actions? This is work led by my students, Xingyu and Yufei. So the first approach is what that you might think is what we already discussed. You can use a latent vector dynamics model. So compress the image to a latent vector, concatenate robot actions, input that to latent dynamics model, and then predict what the latent vector will look like in the next time step. And we already saw the latent vector dynamics models do not inherently encode any environmental structure, which can make generalization difficult. And so we're going to next discuss some other methods that encode more environmental structure and might make learning easier. One alternative approach is to learn a pixel dynamics model. This is, so if you could take an image, encode that, and then input a robot action and try to predict what the next image will look like. This is work that was developed a lot at Berkeley, and for cloth manipulation in particular is explored by Ken Goldberg's group, including Daniel Seda, who's now doing a postdoc in my lab. And so what's nice about this approach is that unlike a latent vector, it actually captures the 2D spatial structure of the observation. However, pixel dynamics might not sufficiently capture the underlying physics of the cloth. So an alternative approach that we're going to explore is to learn a graph dynamics model. So given a point cloud observation of the cloth, we will try to estimate the mesh of the cloth. Then we'll use a graph neural network dynamics model to predict how this mesh will change in response to a robot action. So meshes are a nice representation for cloth. They're often used in the graphics community to model the cloth physics because they basically represent the cloth as a set of points connected by springs. And you can use the mesh edges to capture these different interaction forces, spring force, gravity, collision, friction, things like that. So on the other hand, there's some challenges to a dynamics model, a mesh-based dynamics model for cloth. So the first challenge is that we don't get to see how the points that we observe are connected on the underlying cloth mesh. We just see a big point cloud. And so that's the first challenge, is we don't know where the edges are. The second problem is that we don't know where the nodes are. We don't even see most of the points on the mesh due to self-occlusions. We only see the points that are visible to us on the outer cloth surface. And so, so how should we handle occlusions? Well, the best solution is to estimate a distribution over the full configuration of the cloth, including uncertainty over the occluded regions. And we're exploring something along these lines in ongoing work, so stay tuned for this. In this project, though, we're just going to try to make a very simple point, which is that if you combine graph dynamics with a very simple approach for handling occlusions, you still do significantly better than pixel dynamics or lane vector dynamics or model-free policy. And so what is this very simple approach to handling occlusions? Well, we're going to first learn to estimate how the visible points on the cloth are connected. And so if you look at this image on the left, you can see that this pair of points are connected on the underlying cloth mesh, whereas this pair of points connected in red are not directly connected on the underlying cloth mesh. They're just kind of near to each other because of how the cloth is folded. Does everyone see that? Maybe if you can sort of nod your heads or, okay, cool. So I guess some people see it. Great, excellent. And so we will next create a graph based on the estimated connectivity of the visible points. So here is sort of like a full graph, sort of a cartoon example of what that might look like. And we call this a visible connectivity graph. And then we're going to learn a dynamics model over this graph of visible points. We call this visible connectivity dynamics. Okay, and the dynamics has to somehow maybe implicitly learn to take into account the partial observability of the cloth. Again, it's a fairly simple approach for occlusions. There's more sophisticated ways to handle occlusions, but we're sort of, we're leaving that for future work. So, so here's how our dynamics model works. Given an observation of the cloth, we extract a voxelized point cloud, and then we're going to try to estimate how these points are connected in the underlying mesh. So we're first going to connect all nearby points by edges, and then we'll use an edge prediction GNN to a graph neural network to predict which pairs of nearby points are connected by edges on the underlying cloth mesh. We then input the estimated mesh into a dynamics graph neural network, which predicts how the mesh will change in the next time step in response to the robot actions, and then we feed that back into our model. Okay, so how do we predict which points are connected on the underlying cloth mesh? So we basically frame this as an edge classification task. We start off by connecting all nearby points by edges, and then we do the standard graph neural network thing, which is we encode each node and edge as a latent vector. We perform message passing between nodes to edges, edges back to nodes, back and forth, and then we decode each edge into a continuous number between 0 and 1, and which we interpret as a binary prediction of whether that edge is a mesh edge. And so we train this in simulation where we have the ground truth of the edges for the cloth, and we're going to transfer it to the real world. Next, we have a dynamics graph neural network, which takes as input these two sets of meshes. The first is where all nearby points are connected by edges, and the second is where nearby points, where we connect nearby points based on the estimated mesh edges using the edge prediction GNN that we just described. So we input these two kinds of meshes into a dynamics graph neural network, and we do the same thing, encode, message passing, decode, and the output this time is a predicted acceleration on each node of whether, how that node will move in response to the robot actions. Okay, so how do we plan with this model? So first we need a reward function. In this case, we're mostly going to be focusing on the smoothing task. And so a good reward function for smoothing is just to say, what's the total covered area of the cloth? So we imagine that there's a sphere on each of the nodes, and we project these spheres into a plane and compute the total covered area of the projected spheres. The next thing we need is a planning method. In this case, we'll use the simplest planning method, which is simple random shooting, which is where we sample n pick and place actions. In this case, we just search over a horizon of 1, actually. We simulate the effect of each action with our dynamics model. score each action based on the predicted reward, and then choose the action with the highest predicted reward. This is one of the simplest planning methods. There's much better planning methods out there, but the point of this project is that a graph dynamics model with a very simple approach for handling inclusions and a very simple approach for planning still outperforms pixel dynamics or lane vector dynamics or model-free policy. Okay, so we trained this in SoftGym, which is wrapped around the NVIDIA Flex simulator that we talked about before. We trained it with 2,000 random pick and place actions. Note that the baselines are all trained with over 100,000 pick and place actions. So they're trained on over 50 times more data than our method. And we did this to make sure we were really being fair to the baselines. We use a voxelized point cloud as input to the graph dynamics model, which allows us to really easily transfer between simulation and the real world because we voxelize the same in both sim and real. Okay, so we're going to learn one graph dynamics model, so just one set of weights, and we'll apply, and we train this in simulation and then evaluate on these 3 different kinds of cloth, different materials and shapes. And here you can see the results. So on the left, you can see the actions that the robot is taking. On the bottom right, you can see our prediction of how the mesh will deform in response to the robot action that we've selected. And then on the top right, here you can see the different actions, some of the different actions that we're evaluating. The arrow represents the pick point and the place point, and the color represents how good we think that action will be. So green is, we think it's going to be a very good action. Red is, we think it's going to be a bad action. And you can see that our method is able to nicely generalize and be able to unfold these different types of cloth, different materials and shapes as well, even though it was only trained on a square cloth in simulation. So skip over this. So here is our quantitative evaluation. So the x-axis is how many actions each method is allowed to take, and the y-axis is the improvement over the initial configuration. So 0 means it did nothing, 1 means it's perfectly flat. And this is the performance of the model-free policy. Here's the performance of using latent vector dynamics. Here's using the pixel dynamics method. And here's the performance of our approach. So you can see that we're able to more quickly flatten the cloth in a smaller number of actions. But one thing that's additionally really nice is that even if you only train this method on square cloth, you can evaluate it on a rectangular cloth or on a t-shirt. And you can see that our method shown in orange still works well on these different shapes of cloth. And I think that's probably because it's hopefully capturing something intrinsic about the way, the sort of structure of how the cloth deforms that allows it to generalize to different cloth shapes. And I think also the fact that it's sort of point cloud based kind of helps with that as well, because you're sort of just reasoning about interactions between points. So in conclusion, we learned the visible connectivity dynamics over the visible part of the cloth. Our mesh-based dynamics model better models the cloth physics, or at least leads to better performance compared to better previous approaches. And we demonstrate zero-shot material transfer for cloth smoothing of different materials, even though we only train a single model for this task. Okay, so so that's some work that we've done on learning a cloth dynamics model. Yes.
Dave, this is really impressive. And I wanted to ask you, is there much of a penalty in terms of computation time?
Yes. Yeah. So actually, it takes us currently 15 seconds to plan each pick and place action. And we're only planning over a horizon of 1 step. 1 step planning is actually not really sufficient for all possible cloth manipulation tasks. There's many you can come up with where you have to reason further into the future. And so, yeah, there's a huge penalty in terms of computation time because you have many particles that you're simulating where each one will be. And so there's some ongoing work that we're pursuing. You can sort of imagine kind of different fidelity models, some that are like faster and less accurate, some that are slower and more accurate, and kind of trying to integrate them together.
Okay, good. Because I mean, that's exactly. I'm sure Ellen's thinking the same thing I am, because that would be really interesting to, if you've explored varying the resolution and the fidelity of the models.
Yeah, exactly. Yep. Stay tuned for its ongoing work. Yeah, great question. Any other quick questions about this part?
I have a quick question.
Yeah.
I was just curious whether you think that the VCD method could apply with actions other than pick and place, and whether you think that would be an interesting future direction.
Yeah, that's a great question. I think it depends what you mean by actions other than pick and place. So if you, I guess I would say that if you mean actions like, sort of, let's say you want to hang a cloth on a hanger, that's sort of a little bit more than pick and place. It's sort of a trajectory you have to follow. It can, pretty sure it can handle that. If we're talking about, say, flingbot type actions, you pick up the cloth and try to fling it out. I'm not sure if using VCT is necessarily the best approach for that. It's sort of this, I guess, one very dynamic action that has a large effect on all the particles, and that it might not be quite as suitable for. Although on the other hand, I guess the exact position of the particles might not matter so much in that case. So it's hard to say. Yeah, great question.
I have one really quick one as well, if you don't mind.
Okay,
have you tried? Oh, sorry.
One. Yeah, go ahead.
Sorry.
Yeah.
Have you tried using different goal or cost functions with the with the mesh models, and how does that work? Because it I'm curious how well it works if you define like a folded state with your particles or something along those lines.
Great question. Yes, you can do folding with VCD. It works pretty well. The reason we didn't really highlight that in our paper is that we couldn't outperform the next method that I'm going to show, which uses a different approach. And so we kind of, I guess, didn't feel like emphasizing that, I guess, because we sort of would recommend this next approach for folding instead. But kind of, I think there's opportunities to combine them in the future. Yeah, great question. Okay, cool. So next I'm going to talk about how can we actually learn a model to fold the cloth. This is work by my students, Thomas and Sujay. And so in this task, we're going to define folding as a series of sub-goals that the human provides. So the robot's not going to have to figure these out. We sort of tell the robot that these are the sub-goals that it has to follow for the folding task. And we're going to learn a goal condition policy that takes as input the current observation and a sub-goal and outputs an action. And we want a policy that can decide whether to use bimanual or single arm manipulation depending on the task. Okay, so one sort of common framework or architecture for robot manipulation is to input an observation and a goal into a policy, and the policy outputs robot actions. Since this is consists of pick and place tasks for folding, what works a little bit better is instead of directly outputting raw robot actions, you can output the pick points and the place points. But we found that there's still some, this approach still doesn't work as well as we would like. And I think that's because this policy has to do too much. It has to jointly reason about the relationship between the observation and the goal, and also where the robot needs to grasp the cloth to achieve that goal. So our main insight is to separate these things. We first want to infer the desired object motion. So how should the object move to achieve the goal? And then we can infer the desired robot actions. How should the robot move to cause the object to move in that way? Okay, so let's sort of break those parts down. So the first thing we're going to do is estimate correspondences between the object and the goal, which we call flow. So given an observation of the cloth in one configuration, and the goal, which is assumed to be in this case one action away from the observation, we want to predict where each point in the observation moved to in the goal. So here's sort of a map. Each of these lines is like an arrow, which showed where that point in the observation moved to in the goal. And so we're going to input the observation and the goal into a flow network, and it's going to output these vectors which show the correspondences of where every point in the observation has moved to in the goal. This is building on top of previous architectures used in optical flow tracking. So it's typically used in computer vision if you have subsequent video frames to say where did every pixel in one video frame move to in the next video frame. In this case, it's where did every point in the observation move to in the goal. And we train that in simulation where we have the ground truth. Okay, so given the observation and the goal, we can input that to our network and output this flow image, which gives the correspondences between the observation and the goal as a flow image. And then we'll input that flow image into a pick net, which is going to output the pick points of where the robot should grasp the cloth. And then we're just going to query the flow at the pick points to get the place points. So what does that mean? So suppose that here's our observation and the goal, and these are all the vectors of estimated correspondences between the observation and the goal. And we suppose we pick these 2 points as the pick points, then we can look at just the other end of the flow vectors, and that basically gives us the location of the place points. So we don't need to learn the place points separately, we just query the flow. The other thing we can do is switch between single arm and dual arm actions. So the way we do this is suppose that we make predictions about how each of these arms should pick in place. And if the pick points are within a given threshold, then we just merge them together into a single arm prediction. This is something that can't be done as easily for methods that kind of discretize the pick location or place location. But since we're outputting them in a continuous fashion, we can just sort of set this threshold and merge the pick points if they're within a threshold. Okay, so the next thing that we explore in this work is how do we know when to progress to the next subgoal? So for example, the robot might try to go to the first subgoal and might make a mistake and need to take some corrective actions. How do we know when we're ready to go to the next subgoal? In this case, we use flow as well. So basically, we can take the observation and compute the flow magnitude between that observation and the current subgoal. When that flow magnitude is below a given threshold, that means that we are now sufficiently close to that subgoal and we can move on to the next subgoal. So to summarize, we incorporate this idea of flow in 3 different ways in our method. The first is we explicitly reason about the relationship between the observation and the goal and produce a flow image. The next is we determine the place points for the robot action by querying the flow at the pick points. And the third is we use the flow magnitude to decide when to progress to the next subgoal. So as before, we train this in SoftGym and transfer it to the real world. In this case, we use depth images as inputs, so its material transfer is pretty easy. And so to kind of summarize the main takeaway of this project, we are inputting, as opposed to previous work that will directly output robot actions or pick and place points, we are first inferring the desired object motion as this flow image, and then which indicates how each point in the cloth itself should move. And then we bring in the robot and say, what action should the robot take to achieve these desired cloth motions? Is that main idea kind of clear to everyone? Or yeah, okay, some nods. Great, excellent. So here's some videos showing our robot in action. So on the top left is the final goal, but remember that we're actually inputting this as a sequence of subgoals. And you can see the robot is able to pretty reasonably execute each of these subgoals. Here's a case where it's performing dual arm actions. So it's just output 2 pick points that are far enough apart that they don't get merged together. And you can see it's able to perform different actions pretty reasonably. So the top row is the goal that was input to the robot, and the bottom is what was achieved. In this case, the biggest failures are actually sim to real gaps. You can see our sim results later, they look much better than this. So we were talking with Ken earlier about trying to better calibrate simulators to close the sim-to-real gap, and so that would definitely benefit us here. And we, like before, are able to actually train on a square cloth and generalize pretty well to a t-shirt. And so here you can see our results on a t-shirt. Again, the top row is the goals and the bottom row is what was achieved, which is not perfect. But again, given that we didn't actually train on t-shirts, the generalization here is pretty nice. And I think it's because reasoning about correspondences between things is something that actually can generalize well. This was actually shown already in the computer vision community that optical flow networks for video tracking can actually generalize pretty well to new videos that they weren't trained on. Here's some quantitative comparisons. So the x-axis is the inference time. So faster is to the left. The y-axis is how the average particle position error. So lower is more accurate. And you can see that our method on the bottom left is both very fast and accurate. So that's kind of where you would like to be. It's mostly fast because it's a model-free policy. So it's just spitting out robot actions at a high rate. Here you can see the results in simulations. You can see our results on the left compared to the goals on the right. You can see there's a very close correspondence between them. So which sort of shows that the remaining errors are mostly the sim-to-real gap. Here you can see the output on the right of running one of the state-of-the-art previous methods for this task. And you can see that the results are qualitatively worse. So it's not just a matter of, you know, sort of just some numbers in a table. You can see that it actually performs worse folding from a qualitative perspective as well. So to conclude this section, we have a novel flow-based approach for bimanual goal-conditioned cloth manipulation, which allows us to explicitly reason about desired object motion, and then we infer the desired robot motion to achieve that object motion, which allows us to then successfully perform cloth folding in the real world. Okay, so that was this project on cloth folding. Next I'm going to talk about very briefly a related idea that we've explored for articulated object manipulation. This is a project that was led by my students Ben and Harry. I think Harry is on this call, is previously a student in Ken Goldberg's group, so we're definitely benefiting from all the training that he had in Ken Goldberg's group. And including, among other things, how to make a very nice video, which you'll kind of see the choreography work later. So, we had this kind of idea for cloth manipulation that we should separate out the object motion, meaning how the cloth should move, from the desired robot actions, how the robot should move to achieve that object motion. We're going to apply that same idea here. So the task here is how can we learn to articulate unseen object categories? So here's some examples of different articulated objects. Articulated means that it has typically a hinge or a prismatic joint that the object moves, although in the definition that we use from a certain data set, it also includes objects with lids that you can take the lid off. So it's kind of objects where we focus mostly on one degree of freedom. But the key here is that we've never seen these object categories before, and we want to learn how to open them. And so given that we don't know anything, necessarily the kinematic structure of the objects, how can we figure out how to open them? And so what we're going to do is the following. So let's say here's an articulated object. We want to first infer the desired object motion, which is how would this object move if it were to be opened? We estimate this as a set of vectors coming out of this object, which essentially is the affordances of this object. And so that's the desired object motion. And now we can say, given these vectors, how should the robot take an action in order to manipulate this object? And actually that part now is pretty easy. We can just use motion planning and some simple heuristics to achieve that. So all the learning comes in the first part of predicting how the desired object motion of how would each point on this object move if it were to be articulated. And so given a model that we train over many articulated objects, we can then apply it to these unseen object categories in the real world. It was trained in simulation, and you can see that the robot is now able to articulate each of these objects. This is again zero-shot sim to real transfer. So just to clarify, this is one model, so just one set of weights, not a category level model applied to all of these objects. And so this is again applying this insight that we should separate out the desired object motion from the desired robot actions. Cool. Okay, and so and the remaining time, I'm actually going to talk very quickly about this last project, which is how robots can grasp cloth edges and corners. And this is work by my students, Thomas and Aurora and Thomas. So the task here is how can we teach a robot to grasp the edge or corner of a cloth? So in this case, by edge, I mean sort of the hem of the cloth, and as opposed to these other things that look like edges, but they're really just folds in the cloth. And this is an important task. If we want to do things like folding or flattening the cloth, you have to actually grasp the true edge of the cloth. Okay, so the approach that we take is actually largely inspired by related work by Ken Goldberg and led by a few of his students, including Daniel Seda that I mentioned before. And so the basic idea from this previous work is to train with this colored marker in red on the corner of the cloth, and that's used to get the ground truth. The input to the method is a depth image that doesn't see the color, and we just use they were just using the color to get the ground truth of where the corner is. So it's finding like kind of this corner location. In our approach, we're going to do something similar. So we're going to input a depth image to a segmentation network that's going to output the corners and edges of the cloth. So we're going to color the cloth, corners and edges, these different colors, and use that to get ground truth labels. But our network only sees the depth image, not the color. So it can be applied to other cloths with different colors. Now, there's one difficulty, though, when we try to apply this, which is you also have to reason about directionality. So suppose you want the cloth to grasp this edge. So here's, say, a predicted segmentation of a crumpled cloth and where the edges are. Should you approach this edge from this direction or from this other direction? So that's kind of an ambiguity. And the way we resolve that is by applying this trick again. So here we're actually going to also color the inner edges in green. So now we know where the directionality from the outer edge to the inner edge, which can tell us what direction to grasp the cloth. Now let's dig a little bit deeper into this. Suppose this is our predicted segmentation of the cloth, corners in blue, outer edges in yellow, inner edge in green. So let's zoom in on this region here. And suppose we apply this idea. Where should we grasp the cloth? Let's grasp it in the outer edge in yellow. What direction should we grasp it? We'll grasp it in the direction from an outer edge in yellow to an inner edge in green. But there's one problem. What about these red arrows? That's also an arrow from a yellow region to a green region, but they're not the corresponding outer and inner edges. Those parts are just near to each other because how the cloth is folded. And so what we do is we're going to reason about uncertainty. So given some point that's an estimated outer edge in yellow, we're going to find the directions in the neighborhood to all the nearby inner edges. And you can see that the directions in this point in many different directions. And so there's high uncertainty. Whereas on this point here on the side, there's just one direction in this neighborhood to the nearby inner edges. And so we can estimate this directional uncertainty, and that'll allow us to much more robustly grasp the cloth. We train with just 8 minutes of video that kind of looks like this. It's very easy to collect. And so here you can see our results. So we have this crumpled cloth. We segment the cloth, find the edges, corners, outer edges, inner edges, reason about grasp directions, directional uncertainty, and then we go and grasp the corners. And we can do this for different corners, and here we're grasping different edges. And it actually, you can see it works pretty well in different cloth configurations. And I'll skip ahead to this example where we have this cloth with different textures, materials, and sizes, and the method is able to generalize to these different cloths as well. mostly because it's a fully convolutional depth network, so it's sort of inherent in the architecture. Yeah, we have some baselines, but I'll sort of skip over that, and ablation, so which show that the different components of our method, directional reasoning and uncertainty reasoning, both make a very large difference in performance. If you remove them, you get a very large drop in performance. Okay, so our method distinguishes true cloth edges from folds. It selects a grasp based on the estimated directional uncertainty and achieves robust grasping of crumbled cloth. Okay, great. So what are some takeaways here? We started the talk with this question: how do we bridge the gap between perception and planning? And so let's think about what we did. In the first project, we used a graph to reason about the relationship between different object parts. In the next project, we reason explicitly about the relationship between the current state and the goal. And in the last project, we reason about the relationship between the outer edge and the inner edge. And so what ties all these projects together is reasoning about relationships. I think relationships are actually very important for many robotics tasks, but they're not really emphasized as much as they should be in the machine learning community. And so I think reasoning about relationships should take a higher precedence in many machine learning tasks. In the future, I'd like to extend this idea to representation learning for deformable object manipulation in many other types of situations. Here's some examples of deformable objects, meaning objects that can somehow change their shape as a person or robot interacts with them. And so here's, again, this slide I showed at the beginning. Unfortunately, I didn't have time to talk about all the different projects in my group, but you can feel free to ask me later. Some things I didn't have a chance to talk about is on the top right, we're using tactile sensing to slide along the edge of a cloth using offline reinforcement learning. On the bottom, we're learning to grasp transparent and specular objects and clutter using multimodal transfer learning. This project builds on DexNet, specifically FCGQ CNN. On the bottom right, we're learning to pour transparent liquids into transparent cups using unsupervised image translation, and this should say ICRA 2022. Yeah, so I definitely want to make sure to thank all of my fabulous students, without whom this work wouldn't have happened. I also didn't have a chance to talk about my work on self-supervised learning for autonomous driving. So can we learn from large unlabeled data sets for autonomous driving? We've applied this idea to learn many different perception tasks from large unlabeled data sets, as well as active learning with novel sensors for autonomous driving called light currents. And so you can ask about that later. And here are the students who worked on those projects. And so again, I'd like to acknowledge my students as well as my very generous sponsors. And I'll end here, and I'm happy to take any questions. Thank you.